Good evening, and tonight is a session for physics GCSE Year 10 staff held by Mr. James Ridd von Kunvig Comprehensive School in Bridgend and Mrs. Jane Owen in Penglai School, Aberystwyth. So tonight is a culmination of looking at past paper for foundation and higher. In fact, we're going to look at 2022 paper, and we're going to walk you through for the specific revision sessions that we did before, including circuit electricity, generation of electricity, domestic electricity, and waves. And we're going to walk you through the exam paper, but the one that we're not going to do because we haven't the energy transfer one, making use of energy heat transfer. Okay, so without further ado, I'm going to allow James to start and walk you through, and then I'll catch up with you later.
Thank you, Jane. As was mentioned, this is the 2022 foundation paper for Year 10 Physics, Unit 1. So, as mentioned, I was covering the waves content, or the features of waves, to give it its proper title. And I'm going to look at question 2 now in this paper, which relates to that content. So, a teacher demonstrates waves using a ripple tank. She changes the frequency of the waves produced, and the class observes the effect on their wavelength. You may have seen this setup before, then again you may not have. Essentially, a light shines down on water in a tank. That tank has a glass bottom, and then as the light shines through the water and the glass bottom, the waves can be observed on maybe a sheet of A3 paper or on the bench below. It's a nice little demonstration for investigating waves. Next, the class investigates the link between frequency and wavelength using a virtual ripple tank simulation. The table below shows the results. Now, always just spend a moment looking at the column headings. Very important to see what we've got here. So we've got frequency, we've got 1 divided by frequency, and we have got wavelength. Part A, plot the data on the grid below and draw a suitable straight line. Good news is, if you can plot graphs, then you're going to be picking up some easy marks, whether it's biology, chemistry, or physics. It's such a crucial skill in science because there are 3 marks on this paper, could be 4 marks on another paper, could be 3 marks on another paper, and it all really starts to add up. So you don't want to miss any of those marks. Now, I've already plotted this to save time. And one thing that you've got to be very careful of is paying attention, very careful attention to the axes. So here we've got wavelength and 1 over frequency. Now, it is very easy to make a mistake here and plot frequency maybe and wavelength, but this is not what the graph is asking you to do. The graph is asking you to plot wavelength and 1 over frequency. So we are concerned with these 2 columns. So pay very careful attention to the axes to know exactly what to plot. I plotted this data to save us some time, and I've gone ahead and drawn a line of best fit. In this case, it was quite clearly a straight line of best fit. So with a sharp ruler, no. With a sharp pencil and a ruler, you make sure you do the same thing. Remember, do not connect the dots. It is a straight line of best fit in this case, and it doesn't have to go through every point. It has to really reflect the general trend. Sometimes it could be a curve of best fit, so beware of that as well. But we do not connect the dots unless it is stated in the question. Right, complete the following sentences by underlining the correct word or phrase in the brackets. We're asked to comment on the trend here, really shown by the graph. So it says, as 1 over frequency increases, as 1 over frequency increases, the wavelength, what does it do? Does it increase, decrease, or stay the same? Well, we can see from our graph that as 1 over frequency increases in this direction, then quite clearly, wavelength also increases. We've got a positive correlation, we've got a directly proportional relationship right there. So we can say then As 1 over frequency increases, the wavelength increases by just checking off our graph. Part 2 says, as the frequency increases, the wavelength, well, we've got some options again to choose. And because my graph is telling me about 1 over frequency, I'm actually going to go back to the table to answer this. So I look at the table here, and we look at increase in frequency. So as the frequency increases, that's like reading up the table, isn't it? So as the frequency increases, the wavelength, what does the wavelength do? Well, as the frequency increases, the wavelength, if we look up the table, will actually go down. So as the frequency increases, you can see that the trend in wavelength is for it to decrease. As the frequency increases, the wavelength decreases. Part 3. Use data from the table to state the wavelength of the waves at a frequency of 10 Hertz. So quite simply, using the data in the table, it says here, it's given you a command as well, which is state. Very important word in GCSE science in general and physics in this case. Where a question says state the value, you do not need to make any calculations. So we go up to our table, we find 10 Hertz, and we can see that the corresponding wavelength is 2 centimeters. So we'll write that in, 2 centimeters. Check your unit, it's in centimeters, so we know we're fine just to pop a 2 in right there. Use the equation wave speed is equal to frequency times wavelength to determine the speed of the waves at a frequency of 10 Hertz. Wave speed, V, I could have written down all of it, but I'll just use V for velocity or wave speed, is equal to frequency. In this case, it is 10 times 2, giving us a wave speed of 20 centimeters per second. There may have been a temptation or a requirement to change the unit of measurement here, depending on what the question was asking us to present our final answer in. In this case, it's centimeters per second, so it's okay for me to use 2 centimeters because that's ultimately what the unit's going to be, is in centimeters per second. Now, were it to be the case that it was meters per second, we'd have had to have changed that 2 into meters, so that 2 centimeters into meters, which would have been 0.02 meters. Just a point worth mentioning. Part B then, this is all to do with satellites. Electromagnetic waves are used to communicate with satellites. Some satellites remain above the same point on the Earth to allow constant communication. Complete the following sentences about communication satellites by underlining the correct word or phrase in the brackets. Electromagnetic waves are transverse waves. I'm highlighting this, but actually that's pretty poor practice. I should underline as the question is instructing me to do. So make sure you listen to those commands as well. It's quite clearly stated and underlined, so that's what I should be doing. TV signals are sent to satellites in geostationary orbits using microwaves. Now, as we went through in the content when I went through the tutorial on features of waves, microwaves are used to communicate with satellites because they effectively penetrate the upper atmosphere. Radio waves tend to bounce off the upper atmosphere and therefore are not very good for communicating with satellites in space. These satellites orbit above the equator of the Earth. Next, a satellite orbits the Earth in a circular orbit once every 24 hours. The radius of its orbit is 42,164 kilometers. Use the equation circumference of a circle is equal to 2 pi r, which you might recognize from maths, to calculate the distance the satellite travels in one orbit. So the circumference then is equal to 2 times pi times r, which is going to be 2 times 3.14 times r, the radius, which we're told is 42,164. Now again, no need to change any units because the answer is required in kilometers. This is already, look, in kilometers. Therefore, I can just quote the answer as 264,789, 264,789 kilometers. Okay, moving on. Use the equation speed is equal to distance divided by time to calculate the speed of the satellite in kilometers per hour. So we know our distance from the previous part of the question. So this is going to be equal to 264,789 divided by 24, giving us an answer of 11,033. Now again, no need to change anything because it's asking for the answer in kilometers per hour. So that means my distance needs to be in kilometers, which it is, and my time needs to be in hours, which it is. You know, were to say something like meters per second, it's not likely because it wouldn't be a sensible unit of measurement. But were to do that, then you'd have to convert the kilometers into meters and the time, which is in hours in this case, into seconds. But it's possible and it can be done. But once again, Mr. Ridd is making the point of saying, make sure you check the unit of measurement. Maddie suggests, she's always suggesting, that the satellite orbits at the same speed as a point on the Earth's surface moves, so that it always stays above the same point on the Earth. Explain whether or not you agree. Well, we disagree with Maggie. I know, controversial, huh? We disagree. And the reason is that although the time is the same, okay, I'll put a full stop here. Although time is the same, the distance is smaller at the surface, well, smaller at the Earth's surface. And that should suffice. Yes, you know, both the point on the Earth's surface and the satellite take the same amount of time to complete one orbit. However, if you imagine maybe a little diagram to just illustrate and hammer this point home, this is the Earth and this is our satellite. If this is a point on the Earth's surface and this is our satellite, then obviously the satellite is going to cover a greater distance in one circumference than the point on the Earth's surface. Therefore, if it covers a greater distance in the same amount of time, it must be traveling at a higher speed and not the same speed as Maddie suggests. Okay. And let's skip ahead now to a question on generating electricity, which was the other topic that I covered in the tutorial that I did recently. Have I gone too far? Sorry, I have as well, haven't I? My bad. Yes, yes. So number 4. Sorry. So this one is describe the advantages and disadvantages of generating electricity from coal, nuclear fuel, and wind. If I'm perfectly honest, this is a dream of a question, because it is literally just asking you to say what you know about these energy resources. It's not asking you really to compare or contrast these energy resources, which is a harder skill. To explain the advantages of one energy resource over another, for example, requires for you to think about both of them simultaneously and think about how they compare. In this, we're just asked to state the advantages and disadvantages of all three. I will just read through this quickly. All right, so coal is non-renewable. Disadvantage, that's a sad thing. Okay. However, it's reliable. Yay! It is very reliable. It's one of the reasons we still use it so extensively today. It also produces large amounts of electricity, which is, you know, its biggest pros, really. It's a fossil fuel that produces CO2, which contributes towards global warming, as it's a greenhouse gas, and sulfur dioxide. Now, sulfur dioxide is problematic, especially when burning coal, because sulfur dioxide can cause acid rain. Although great measures have been taken over recent years to reduce the amount of sulfur dioxide released into the atmosphere and therefore reduce the amount of acidity in the rain. CO2 is a greenhouse gas, we mentioned that, contributes to climate change. And then another disadvantage, mining coal damages habitats, and transport of coal has significant environmental impact. So it's all there. You wouldn't need to say all of that for all of the marks for coal. You maybe would be expected to give 2 advantages and maybe 2 disadvantages. Nuclear then, again, disadvantage is non-renewable. However, it is reliable. So in that sense, coal and nuclear are similar. Produces very large amounts of electricity, but a big advantage here is no greenhouse gases. However, there's always a catch, isn't it? Nuclear produces nuclear waste, which is highly radioactive for very long periods of time, making it costly and difficult to store. Currently, our policy with nuclear waste is to just sort of bury it underground and sort of keep it secure, which isn't a great long-term strategy. Then finally, with wind, it's renewable, so in theory, it should last for an awful long time, 4.5 billion years. But you know that should be sufficient. It doesn't produce CO2. It's sounding pretty good for wind. There's no fuel cost. God, this is amazing. However, what are the downsides? Well, it's unreliable. You can't rely on the wind, obviously. It doesn't produce a great amount of electricity either, unless you have a very large number of turbines. So the energy density of wind is quite low. And by that, I mean that to produce the same amount of energy as maybe a fossil fuel burning power station, you need a very, very large area of land, and it causes visual and noise pollution. People don't want them on their doorsteps. Part B, Sankey diagram below shows the energy transfer for a coal-fired power station. Okay, we've got input energy of 15 megawatts, and then we've got energy output to the national grid of 5 megawatt hours, and wasted energy, well, we don't know what that is. That's just a blank for now. And surprise, surprise, the question asks us to complete the diagram opposite to show the wasted energy. It would have been opposite normally in an exam paper. In this case, it is above. So we got 15 going in. We got 5 converted to useful energy. So that means we must have been wasting 10 megawatt hours of energy as heat and sound. Use an equation from page 2 to calculate the efficiency of the power station. This is so important. Use an equation from page 2. You go to page 2, which I kind of begrudge doing because I've got to scroll all the way up, but we've got to find it. And if you find the equation for efficiency, which is here, all right, we take that back and we write it down. Now, this question isn't giving us the formula. It is telling us to find an equation. So we say efficiency is equal to useful divided by total. I'm writing it in shorthand. You may want to write it out in a bit more detail, times 100 for a percentage. Just by finding the correct formula and writing it down, I can't explain to you how crucial this is. You are going to get a mark almost certainly for this. The examiner wants you to be able to find the right equation. You could literally draw a unicorn at this point now and still pick up 1 mark. So our useful energy is 5. We're not going to draw a unicorn. I'm going to finish the question properly, but you get my point. Times 100%, and that's going to end up as 33% efficient. And just to explain what that means in words, it means 33% of the energy supplied is converted usefully into electricity for the national grid, and the rest is wasted. How are we doing for time, Mrs.
We've got basically 1 minute until we turn over. So shall we do the foundation paper, and then we've done it properly then?
Okay, yeah, absolutely. So
okay.
Shall I turn over to you now?
Turn over to me, and then if we have time, we'll do the higher.
Yes, okay.
Okay.
Right then, so I am going to stop sharing. And then live.
And then I'll share my screen here. Okay. All right. So I think I'm showing what I've got now, and I'm going back to question 1 of the foundation paper. And I'll go through domestic electricity and circuit electricity. And interestingly, the circuit electricity, which is the end question of this, is actually question 1 for the higher. So bear with us if you are higher candidates, and foundation, carry on. Okay, so here we've got domestic electricity in the UK is supplied to houses at a voltage of 230 volts, and it's an alternating current supply. So we've got to tick one of those boxes below the diagram which shows the voltage from an AC supply, an alternating current. Well, it has to be number 1, because number 2 and number 3 are showing direct current supplies where the current is constant. In the second case, it's positive. In the third case, it's negative, assuming that dotted line in the middle is at 0. And the only one where the current is changing and alternating, going from positive to negative repeatedly in cyclic way, we say sinusoidal, is the first one. Okay, moving on. To use electricity safely in the home, some safety features are used. We've got to draw a line to match the safety feature in the list on the left with its action on the right. So just have a quick glance. We've got fuse, we've got RCCBs, we've got earthwire, and we've got MCBs. And then try and match it with the action. Now the fuse one is the only one here that would melt if there's too much current in the circuit. So match those two up. The earth wire is the one that provides a low resistance path to the earth for the current to go in. Okay, so a massive amount of current is able to flow, low resistance path, and it can zip down all the way to ground, the current electricity. So we've got to sort out the miniature circuit breaker and the residual current circuit breaker. Now the miniature circuit breaker acts very like a fuse, that if there's too much current flowing, then it would switch the circuit off. Whereas this residual current circuit breaker will effectively look at the difference between the live and neutral currents. And as soon as there's a difference between the two, because it's sensing that there's current going down the earth, then it flips the RCCB to switch the circuit off. Okay, moving on from there. Now notice you've got 3 marks for this. Okay, so it's not, one for every one. It's basically 3 marks for all of them right. And probably if you get 2 of them correct, you'll get 2 marks. Okay, so one purpose of safety features is to prevent fires. State one other purpose of safety features. Well, we're wanting to prevent or stop electrocution or electric shocks. Okay, so we can say that. Now the marking point here is for indicating what it does to those electric shocks. It prevents them from occurring. Okay, and James has gone through the waves question. So I'm going to switch now to, and we haven't done a revision session on the heat transfer. So I'm going to bypass that one, but I'm going to keep the answers at the bottom of this so that you can see them at a later date. I'm now going to switch to a domestic electricity. Okay, now it's really crucial here to do, as James has said, read the question and pick out the data and look at the units. Okay, so a biogas generator converts cow dung into biogas, which can be burned to generate electricity. So a farmer buys 3,750 kilowatt hours of electricity per week from the national grid. Okay, so that's going to be an interesting number. He plans to buy a biogas generator, which should reduce this to 750. So by reducing it, that means we're going to make some savings here. So 3,750, it says calculate how many units of electricity he would save per week. Now, all the way at the top, you have got from page 2, you've got all of the equations. So if I just jump up there, okay, right here. Okay, and let's look at, we are going to look at these set of equations here. But it's interesting because we've got there cost is units used times cost per unit. But we might as well kind of like add another little thing here and put savings is equal to units saved as opposed to kind of using, times by the cost per unit. So you're kind of like flipping that equation on its head. Okay, we're using the same one, but we're going to be using that. So let's carry on going down. Sorry. All right, there we go. Okay, so calculate how many units of electricity he could save per week. So let's find how much we would save. So take away the 750 and we've got ourselves 3,000. Now make sure you put the answer. You can put the answer here, but make sure you transfer it onto the answer line. Otherwise, they won't give you the mark. Now they've given you the equation that we had. Saving per week is the unit saved times by the cost per electricity. So if we take the unit saved, that's 3,000, and times it by the cost. Now notice this is in pounds, 0.20, and they want the answer in pounds. So we don't have to convert it into pence or anything like that. We'll just do the calculation as it is. Okay, show you're working, and then you can write what the answer is. So I've got here £600, and I can keep the pounds there and just transfer it to the line. Now, if they did want it in pence, you'd have to times that by 100. But what you mustn't do is kind of like do your £600 there and put pence at the end, because it's not in pence at all, it's in pounds only. So I'm going to put a cross through that. The biogas generator costs 150,000. Now this is another equation that actually is not featured on page 2, and I think it should be featured on page 2, but it's a very useful equation because it works out kind of like, you know, is it worth doing, and how many weeks have I got to kind of like, you know, kind of have it installed before I pay back the initial cost of installing it in the first place. So the cost is 150,000. So I divide it by the savings per week, 600. All right, and I've got an answer of 250 weeks, and I'm going to slot that into my answer section. But please show the working, otherwise, you know, you're not going to get your full marks. Calculate the expected payback time in years. Now they want you to convert that weeks into years. So you know, and they've told you that 1 year is 52 weeks. So 250 divided by 52 will give you the number of years. And that comes out at 4.8 years. They want it in years. So 4.8, or you could put there 5 to round it off. Okay, keep going. The farmer wants the biogas generator to produce at least 3,000 kilowatt hours of electricity each week. He collects 60 kilograms of dung from each cow per week. 1 kilogram of dung produces 0.095 kilowatts of electricity. Calculate how much electricity can be produced from each cow per week. So what we've got to do here is we've got to take the amount of dung, 60 kilograms, and if you know that 1 kilogram gives you 0.095, then you know by timesing it by 60 that 60 kilograms will give you 60 times 0.095. Work it out on a calculator, we get 5.7. You can round it to 6 if you want, but leave it as 5.7 and pop it in the answer line. Calculate how many cows the farmer will need to produce the 3,000 kilowatt hours needed. So 3,000 is what is needed. So for each cow for every week, then let's divide it by 5.7 to find the number of cows needed for that. So 526.3. Okay, now you can't get 0.3 of a cow, so you could round this to 527. You can either leave it as 526.3 or you can go up to 527, but actually they would accept it if you round it to 526. But think about it, you need a third of a cow, you can't, you know, get away with that, so you're going to have a whole cow to give you what's required. Okay, So the table below, now they usually have now for you something to think about. So they'll give you some data and they'll want you to agree or disagree based on the data that they're going to give you. So the table below shows the heating effect of different greenhouse gases they have on the atmosphere by comparing the global warming potential. Now, we haven't taught you that, but they've given you some new information that you're meant to be able to kind of like be able to work with and get data from. If the global warming potential, GWP, is twice as big, the gas will cause twice the heating effect. If it's left outside, the cow dung releases methane into the atmosphere. Okay, and methane gives you a GWP of 25. In a biogas generator, the methane is captured and burned, releasing a similar amount of carbon dioxide, okay, into the atmosphere instead. And look at this, carbon dioxide, it only gives you 1 GWP. Now, Alan suggests that biogas generators are bad for the environment because they release CO2 into the atmosphere. But the thing is that the GWP of CO2, we know that CO2 is bad, but you've got to just look at it, you know, with the data in front of you. So the GWP of CO2 is 1, whereas the GWP of methane is 25 times bigger, or 25. Okay, therefore disagree, because CO2 is not as bad as methane. So they're just asking you just to deal with the data. You don't have to give your personal opinion to the fact that, say, CO2, you know CO2 is bad, and say that it's bad. You've got to just base it on the evidence and the information that's in front of you. Okay, now question 6. Now question 6 is the last question of the foundation and the first question of the higher. And they try to do this so that to give something challenging for the foundation and something to start with the higher candidates, but an overlap. Okay, so this is going to be tricky, but it's going to be doable. A group of pupils investigate the current voltage IV characteristics of different components. The first component they investigate is a lamp. Okay, you know that's a lamp because you've got a symbol there for a lamp, and part of the circuit is shown below. They want you to add a variable resistor and a voltmeter to the diagram. Now, a variable resistor could go anywhere in that circuit, but perhaps it can go here on the right-hand side because there's space for us, but it could literally go anywhere around that series circuit with the ammeter in. They put the ammeter in series, but they also want you to put a voltmeter in. And remember, a voltmeter always goes in parallel, so it can go below the lamp like this, or it can go above the lamp like this, like that. And you'll get 2 marks for that. Now, I know that here, in order to vary the voltage and the current, you have to have a variable resistor because there's only one cell here. Okay, now if there were several cells there, you could get away with putting an arrow through them because you could change the number of cells. But here, in order to change the current and voltage, you've got to have a variable resistor. And a variable resistor symbol is a resistor, but with an arrow going through diagonally. Now, they draw a graph from their results for the lamp, and it's shown. Now, this gets a little bit complicated. One student suggests that as the current through the lamp doubles, the voltage triples. And they've asked you to use pairs of data within the range of 0.5 amp to 2 amps from the graph to explain whether you agree with the student. So go back to your graph and look, and you've got to go anywhere between 0.5 and 2. That's what they've instructed you to do. So if I were you, I would take it and make it really easy for yourself. Choose a current of 1 amp. Go across to the graph and go down and read off what that voltage would be. and then double the current to 2 amps to see what will happen to your voltage value, okay, if you double the current. So it's a good idea to draw it on the graph. You can alternatively take your pairs of data and put it onto your answer, but let's just see what it is and let's compare them. So 2, 3, 4, 5, 6, 7, 8, 9. I'm just going to put those in. It makes this easier then to be able to read it off. So 2.2, 2.4, 2.5, 2.6, 2.8. So this is 2.4 volts, okay, here. And then that increases to 8.2, 8.4, 8.6, 8.89, 8.6 there, 8.4 there volts. Now, to work out what the difference is between those two, it is easier to write it as a fraction and put it into your calculator as a fraction. 8.4 divided by 2.4, you can see by how much it gets bigger. So I'm going to quickly do that. I have already done it. I just want to check it out though. 8.4 divided by 2.4 equals 3.5. Now, this is what we call a factor. So if you increase it by 2, the voltage here increases by 3.5. So clearly, this is not in agreement with what the student suggests. Now, I didn't have to choose 1 and 2. I did it so that you can see it big enough. I could have chosen 0.5 and doubled it to 1. And then you could have read it off like that. But I've decided to do it like that. So you can put all of your values in. So at 1 amp, the reading is 2.4 volts. At 2 amps, so there's my pair of readings, it's 8.4 volts. So I've got to, now this is the trick, you've got to divide the 8.4 divided by 2.4 to see what the factor is, because that's double, i.e. the current doubles, and then what do these two do? They increase by a factor of 3.5. So therefore, disagree. Okay, it's all about linking it back to the question. Explain whether you agree with the students. WJC love this. They love to put something forward for you to prove or disprove using the data that they have given you. So tie it back in to say agree or disagree. There are many different ways of doing this question, and I have put all of those different alternatives there for you to see, along with what the examiner report is about how candidates did this. Okay, use the equation, moving on. Use the equation power equals voltage times current and information from the graph to calculate the maximum power produced by the lamp. So if we go back to our graph, here we go, at 12 volts, okay, that should be a maximum voltage. That's where the graph stops. So that's 12 volts. And then read this one off. Is that 2.5? I think it is 2.5. So that is 2.5 amps. And you know from an equation, there we go, they've given you the equation. And at foundation, it's very rare that you've got to you know, they will give you the equation to work with. Sometimes you've got to go and find it, and sometimes they give it to you, and all you've got to do is put in the numbers for it. If you're doing higher, they'll ask you, you know, they'll expect you to be able to rearrange it to get one of those terms. So power equals 12 volts times by 2.5 amps, and that gives us a 2.0. Oh, hold on. Have I read it off wrong from the graph? I think I have, because look, 2.5 is up here. So you've got to be really careful and don't rush it. Just read the graph properly. So 2.0 and 2.5. So that means every 2 is 0.1. Okay, so I'm going to just divide it off. So 2.1, 2.2, 2.3, 2.4, 2.5, which means that I should have had this as 2.25. all right, amps, because it's halfway between 2.2 and 2.3. So let's put that back in for here. Okay, I'll just do this, 2.25, and we get an answer of 26.4 watts. Don't forget to put it into the answer line. And then the experiment is repeated with a 6 ohm resistor, but the results are lost. So use the equation current equals voltage divided by resistance to calculate the current through the 6 ohm resistor at 12 volts. So you've got your voltage and you've got your resistance. So it's straightforward. 12 divided by 6 equals 2 amps. Okay, and pop 2 there. Draw the line for this resistor on the grid on the previous page. So at 12 volts, the current is 2 amps. So we've got our two plots. At 12 volts, we've got 2 amps. Oh, let's go back. And it's a resistor though. So at 12, it's 2. So I'm just going to take this arrow out, I think. Okay, and just pop the point there. But because you know it's a resistor, you know with a resistor, it will be a straight line going down through the origin. Okay, so I'm going to be very carefully try and draw. It's not very good. So make sure you use a ruler. Make sure the ruler and you use a pencil for all of this so that you can, rub anything out or you can redraw it. And that goes for your plotting. Okay, the plotting has got to be to the nearest half of one of those small squares. And that will give you a constant gradient. Wherever you are along that line, you will still get 12 divided by 2, which is your 6 ohms. It doesn't matter where you are. All right. Okay. So just test that out. It should be 1.5, 9 divided by 1.5. That will give you 6. Okay, 6 ohms. Right. Now, how am I doing? And are there any questions?
Doing fine. Thank you, Mrs. Owen. And there aren't any questions at the moment in the chat. We have got a couple of minutes left.
Okay. All right. I think. Okay. Where shall I go from here? I think. Okay. So we've done electricity. We've got a little bit left. Sorry, I thought we'd finished the question. So we could got enough time to finish the question. All right.
An important point there, always check that you finish the question.
Yes, and check the back cover that there's not a question on it. How many times? Okay, the students are given a, thank you very much, sir. The students are given a sealed box containing another component, but we don't know what's in it. They're asked to confirm whether the hidden component is a diode. So how would they use the circuit shown in part 1 to confirm whether or not it's a diode? Well, you're going to connect one way, all right, and see if you've got a reading. Connect one way and see if you have a current reading. See if get a current reading. Remember, I is for current. Okay. Now, if it's a diode, you turn it around. You can either turn the battery around or you can turn the sealed box around. So connect in reverse. Now, if you did this, then if it was a diode, you won't get any current reading if you got a current reading the first time. So connect in reverse, and if no current reading, then it must be a diode. Because what is a diode? A diode allows current one way only through a circuit. Okay, and you can remember that because the O in diode. So sketch the IV graph, what you would expect to obtain for a diode on the grid below. Well, if it's in reverse voltage, i.e. negative voltage, you won't get any current flowing at all. If it's in positive voltage, all right, you will get a whole load of current flowing after a certain point. So there is a threshold. I don't think I've done that very well. Okay, there is a threshold limit for when the current rises up, and then it's kind of like infinite. So that's a little bit better, but not perfect. Okay, all right, and there we have it. We have done a foundation paper in its entirety, and we have left the mark scheme and the report either below or by the side of the questions. And I think it is, thank you very much from me.
And yeah, thank you very much from me as well, and thank you, Jane, for taking us through that. This has been e-sgol Carlem Cymru sessions, and please check back in the website soon for more content as is created and uploaded. And good luck with your exams.